I will. Okay. Good evening, everyone. Welcome to another exciting talk in our seminar series. Today we have Barbara Blank, who is an associate, soon to be a full professor in NLP and the head of the master's program in data science at IT University of Copenhagen. Barbara obtained her PhD degree in 2011 from the University of Groningen and held faculty and research positions in Denmark, Italy, and the Netherlands. Also, she has recently appointed to be an Alice NLP scholar. Her research interests are broad, with a special focus on technical linguistic variation in NLP and interest in interdisciplinary research. And today, she will talk about a very important topic, learning with scarce and biased data in NLP. Thanks, Barbara. The stage is yours.
Thank you very much. So first of all, thanks a lot for this opportunity here. I'm really happy to visit you virtually and for this opportunity to just talk to you and show you a little bit of what we have been doing recently and some time ago. And yeah, hopefully, we have a nice interaction. So please feel free to interrupt me and just ask questions along the way. I'm very happy to take them as we go along. All right, then, welcome everyone. Thanks for joining the talk. So we'll start off with, browsing over what do I mean actually with learning from scarce and biased data in NLP. And now, of course, okay. So, we typically are interested in machine learning, of learning functions essentially in NLP. It's about learning functions from textual input to some sort of label, some output Y, which can be as simple as a class, or something more structured like a dependency parsing or relations. But one really important issue here is that we typically need human annotated examples, and getting these labels is quite expensive, and not only expensive, it's also a very time-consuming process to get the guidelines and go through the iteration to ensure that we get high-quality annotations. So if you think then about, the label data that we typically have in NLP, in core NLP tasks, then it's actually, if you think about this whole data space out there, we typically have a very small amount of data that's labeled. And so you can think of this as like, okay, a sparsity in the kind of labels we are seeing. This is a big issue, right? And there are ways to circumvent this, but I would like to mention that even in some domains, you might say, okay, well, we have lots of unlabeled text, right? That's easy to get. And we've seen also in recent times that has really pushed the field significantly with pre-training on large unlabeled text corpora. But even then, in quite some of these domains, you might be running into scarcity. And that's something that we are not dealing so much or so well as of yet. So there is also this X-sparsity or scarcity that is becoming more and more important. And so this is the scarcity of the data, but also there's a second part to it, and that's the biases in the data we are dealing with. And so if you think about labeled bias, I actually mean two things. One is selection bias. So here's just an example to illustrate this bias that we are facing by looking at, here are snapshots that I've been doing quite some years ago, 2016. I looked at the Universal Dependencies project and just mapped out what are the languages for which we have additional domain or genre information available. And if we plot these languages times domains, we see clearly that there is a bias towards one of these genres, namely newswire text. So it's important to be aware of this, right, when we also transfer information or use the resulting technology. And we recently looked at this again, my PhD is on Max, looked at a much more recent version of UD now. It's a fantastic project which is growing every half year and has over 100 languages as of last year already. But we're still facing this issue that a lot of the data is actually coming from newswire. So this is this kind of general, the bias in the inputs, so to say, and there is this mismatch that we have models that say work reasonably well in newswire, but then the performance really goes down if you go across domain. Or similarly, we have a lot of English data for many tasks, but we don't have, for instance, a lot of data for Danish, as an example. So this is this kind of bias in, say, the X dimension, right? The shifts that we can see in the underlying distributions. But there's another sort of bias I would like to mention, and this is the bias in the labels. And here, what I mean is, typically we target high quality annotations, but even if you ask experts for some tasks, there might be, disagreement. Even for very simple tasks that we might see disagreement. And so typically here, we assume that our label is just a single ground truth, and we're learning from the single label in order to learn how to do language technology. And I will come back to this in the third part of the talk, showing essentially also that for more objective tasks like post tagging, we do see disagreement between annotators, and we can think about ways of using this. So this is kind of the setup I'm interested in here, or focusing here on. But what can we do about it? Typically in NLP, we are facing a traditional setup where we say are interested in a domain, task, or language, and we train a model, and we evaluate the model or improve that model within the same kind of task. And then if we go to another problem, we're essentially starting from scratch. And so the main question or idea behind a bigger spectrum of this work is to try to adapt or transfer to the new problem. So we want to use some sort of knowledge that we can derive from the original formulation, from the original task or data, in order to help solve another task. And now this is a general idea, right? And we can look at this again from different views. So imagine we're interested in providing technology for social media processing, but we have Newswire, so we face the cross-domain gap. Or similar if we go across languages, cross-lingual gap. But there's also more to this. There's we can try to actually leverage data from other tasks that we might have at hand and use a more multitask learning setup. We will see this is even much broader than just, this applies to many things essentially. Or if we don't have labeled data, maybe there is other sorts of signals out there that are like byproducts and are not so immediately there, but we can also exploit those as fortuitous data sources in order to help bridge or generalize better to new types of tasks. And another view of transfer learning is also this nice adaptation by Sebastian Ruder, originally from Panedol, which divides it up into, okay, do we actually have the same task at hand, right? Is it transductive or inductive transfer? If we are interested in the same task, and it's mostly either learning under domain shift or domain adaptation or cross-lingual learning. But also there's a question of when do the tasks or the data sets appear, and then we might be interested in multitask learning or more the sequential adaptation process, where there's also two ways of looking at this: sequential transfer and continual learning. Just to give this a bit more of a notation here. So when we face from this shift from source to target, and we see, say, different distribution over the inputs, over the feature space, then we typically face this adaptation scenario. If they are in the extreme case, even different vocabularies, we face a cross-lingual learning setup. If we face different tasks, we might think about a multitask learning setup. And now if there is even a time dimension to this we're interested in, we might be even seeing a sequential transfer or even a continual learning transfer, where we are interested in also, not just improving our target task, but also still improving up the original tasks we have been trained on. This is not, a strict separation. They are also overlapping to some degree, but at least this gives us a way of thinking about the bigger picture, I think. And now I want to just highlight something which I think is important: is sequential transfer is now omnipresent. And this is something, in fact, if you look at the NACO 2019 tutorial on transfer learning for NLP, this has actually focused almost entirely on the setup, which means that we are doing the sequential transfer and using, okay, we're doing pre-training, we're getting a huge language model or some other sort of vector representation. and then doing a fine-tuning step with adaptation. And that's mostly what nowadays, when you think about transfer learning, this is what is thought of, right? Many people think about this. But I would like to highlight, this is just, this is maybe now the underlying technology which we are starting off with, but there are many more aspects to this and algorithms out there that we can use in this broader transfer. So transfer learning by itself is much broader than just this snapshot, which is one kind of typology, technology in this framework. All right, another dimension which is important to think of when trying to transfer is also actually what are the assumptions, what is the data that we have available. And here I really like also this survey that recently came out at NACL by Heather Hugall about low resource processing. And they categorized it also across 3 types of data that are available. So we might have task-specific labels, right? In the best case, we have some labeled data for the target, but we might have other data available, not specific for the target, or even just unlabeled data that we might exploit. And so while this categorizes the type of dimensions of resources that we have available across this what dimension, I think it's interesting also to think about when or the timing, right? So when do these sources become available, or what is the assumption that I have currently? So this is linking back to this other typology, right? That either we have all of it available at the same time, or we are essentially in a setup where we are getting the target data or in steps or in a sequence, or even in the extreme case in a streaming setup. All right, so this is the broad introduction, and in the rest of the talk, I had the hard choice to select a couple of studies, so I decided to go into 3 studies here, and I hope that there is something for all of you. Some is a bit older, and some is a bit more recent, so this covers a spectrum of things we have been doing. Yeah, and please interrupt me at any moment if you have any questions. All right, then now I'm moving into the first part. So we'll move first into domain adaptation, essentially, and then go to cross-lingual learning, starting to go already into multitask learning there, but then also come back to multitask learning in the last part. And I will not talk about continual learning in this talk. But this is now work that has been, it's a few years ago now, but with Sebastian. And we were interested, this is something which interests me since a really long time, essentially. And the interest here is, hey, can we actually get better training data for a target domain? And so in a way, it's also, can we train more efficient models by selecting more appropriate data for a target? And the data setup that we are taking here is suppose you're interested in some target domain, like say kitchen appliances, and you have labeled data sets available, right? So this is an assumption that we take now. We have some labeled data for some source domains. And the question now is, hey, how can we actually learn the most relevant data from these set of sources using metrics, right? And notice when talking about the source domains here, I really mean we're actually trying to not see them as these labeled data sets of these, we're actually dropping these domain boundaries. So it's books, DVDs, and electronics, but we here put them all into one pot and are interested in, can we get a better data set which is better fit for the target domain by choosing from this pot of data instances. Now you might say, well, why do you just not train on all, right? Why are you interested even in this setup? Well, one now becomes more important is also for efficiency, but here that's not the problem, right? This is quite small setup still, but mostly it is to prevent also negative transfer. So if we just blindly train on all of the sources, and if they are not relevant for the target, then we might actually see a negative performance, so a negative transfer to the target domain. For instance, if you think about sentiment analysis, and you have, say, a feature word like predictable, that might be, for a book, it's not a very good feature to be predictable, right? But for a kitchen appliance, it might be actually a very good feature if it's predictable, a predictable tool. So this is essentially the motivation. And prior approaches to this typically resulted or used only a single similarity metric in isolation, including, in fact, my own earlier work. And they focused simply mostly on a single NLP task. So in this work, in fact, we were interested in looking across several NLP tasks because we had this intuition, okay, different tasks and domains might actually require different notions of similarity. And that's why in this work, we essentially try to come up with a set of features that encode similarity, but then try to learn to weight them in order to select the data. So that's the kind of key contribution of this work.
So
how do we,
Barbara, I have a question. Maybe this is too early to ask, but can this be also generalized to a multitask learning setting where instead of selecting data, you are selecting tasks?
That's a good point. Yeah, you could actually to kind of divert the setup to the multitask to which head you want to predict. Yeah, you could. Yeah, exactly. Nice idea. So yeah, but here we did it on the data level essentially, right? And now what we're doing essentially is, okay, a set of source domains, right? Like these 3 domains I've shown earlier. We assume we all put them into one pot. And then the idea is, okay, we are learning the features essentially are our similarity metrics or dissimilarity metrics. And then we are learning these weights to rescore these examples so that we can then select M examples and train a model on these M examples only. And now, if you are familiar with curriculum learning, this is kind of a way, it's kind of related. It's not, which is also like, that's more about efficiency in learning and taking the simpler examples first, but at least like the metrics used were also used in curriculum learning, for instance. So here, the main thing then is this Bayesian optimization procedure. So you need a little evaluation data and development data. And what you do is then actually from your data extracting these features and learning these weights in an iterative fashion where it explores the space in order to come up with a good feature weight. So this is kind of a wrapper around your own algorithm, you can say. And now the question is, what are the features that go into this? And yeah, here it's up to the designers, right? Good old feature engineering. But what we did here is essentially starting off from very simple representations. So anything you can think of that represents your instances, like just plain term distributions. How often do these terms or words appear? To LDA topic models or even embeddings, right? And then that are like representations we used. And then different similarity functions. So we took here Jensen-Shannon and a couple of others that we can put into this space. In addition, we here also proposed to look at diversity measures. So we wanted also to add that angle in order to see whether that's important for selection, right? Not just similarity, but also somehow how different the instances are. And here you can think about the type token ratio, the number of types, the diversity in a way of the instances, and so on. All right, now what did we do? What kind of evaluation did we do? So we took in fact 3 NLP tasks. One was sentiment on the well-known Blitzer et al. Dataset, where we have these 4 sentiment domains. And the other was we did dependency parsing and post-tagging on the Sankel data. That's actually English Web 3 bank. And we here ported from English Newswire to these target domains. In the sentiment analysis case, we do like the pairwise, no, sorry, each domain is a target and all others are source in the setup. Now, about baselines, right? So what did we do as a comparison? We are taking M examples to train the system on. And now if these are the target and on the left are the source domains, obviously, the one baseline is just randomly selecting instances, right? But then we compare to two other very simple baselines, which are in fact shown from earlier work also that they work quite well and are quite strong baselines. One is just taking the Jensen-Shannon divergence between the instances and finding the ones which are closest on, I think, dome distributions in this case, if I'm not completely wrong. But the closest M instances according to the single metric, essentially. Now, another baseline is instead of taking these examples, we can actually find the closest original domain and then select from that domain. So this is what we call the Jensen-Shannon domain case, right? So these are the baselines. And then we compare our Bayesian optimization approach with similarity features, diversity, or the combination of the two. So what do we observe? Okay, here are the plots for sentiment analysis. We select 2000, and here we see that, okay, random is actually outperformed most of the cases by already a single metric. But interestingly, and that's my main takeaway here, the yellow one is when we choose the domain first. And the green one is when we choose just from the whole pool. So here, for sentiment analysis, it was better to first find the closed domain and then sample from that. But can we do better by learning the metric, the weights? And we saw, in fact, that in these cases, we could improve over, say, the random baseline or the single metric by looking at similarity or actually the combination of all features were the best performing. So this is encouraging, but still, okay, you could say, what about using all data? How does this compare? And if we do that here in this case and triple the data, we actually see negative transfer. So in this sentiment case, it was actually helpful to do this data selection. All right. Then similarly for dependency parsing, I'm just showing those results here. This is again the random baseline. Now, this is the single metric. What was interesting here is the green line is higher, right? And here, what that means is it was more beneficial to actually choose from the whole pool without regarding the original domain labels than trying to find the closest match and then selecting within those. I think this is because it's more dissimilar in a way than in the sentiment case. But we saw also that, the Bayesian optimization approach, it helped with similarity measure, diversity measures actually, but not the same picture as before, right? It was smaller improvements, and also the combination of the two wasn't so helpful. So it was less clear of a picture. Still some improvement, but yeah, not as much as the simple selection actually was helping already. But there's one more note, and this is now if we train on all of the data, which is with around almost a magnitude more. It depends on the target domain. But actually, we don't see, we see a negative, we see positive transfer from all of the domains in these setups. So it's not hurting as much as in the other case. So here, if training on all would be the best model, essentially. So it's not so much about improvement, but more about efficiency if you care about the smaller model. So yeah, from this part, we showed that these domains and tasks have this kind of different notions of similarity. Although this Jensen-Shannon divergence is a very strong baseline, we can see that there is clear negative transfer for sentiment, but less so for the syntactic task. Actually, for both, we saw less negative transfer. In the paper, we also show, since you are learning these weights, how can you actually transfer them between these setups, right? It's an interesting question. Can you transfer, say, weights learned for sentiment to parsing or post-tagging, right? Or can you transfer them from a more efficient model, like in post-tagging? Can we do it with a cheaper model to get the weights in the Bayesian framework? And yeah, we show some interesting results about that as well. There is some transfer even, but as expected, more between the syntactic task than say from sentiment to dependency parsing. So they do learn some kind of task specific notion here. All right, maybe just one note before going to the next. I think this is what I like about this is that, you know, we see that these domain labels are not so clear cut, right? Because we do see different results. And when we think about domain, it's not always so clear what that actually implies. So we are dealing with some notion of, like, I like about to think about this as a high dimensional space, and we don't even know what exactly the dimensions are of that space. So it's variation around language, whatever that means, genre, domains, social factors, all of that goes into this. And it's hard to tease this apart. But recent work also has shown that this notion still is very important. So finding related data is even important in birth times. So it's a very nice paper from last year's ACL showing that you can do much better if you select data which is closer to your target task. And there's also other work on machine translation and showing that you can identify already in a pre-trained bird model, it's actually clustering very nicely about these topical domains at least. So yeah, just some more additional pointers if you're interested in this kind of work. Yeah, are there any questions to this part maybe?
I have one question actually.
Yeah.
For this data selection, these are executed before training the models, right? It's like the first step.
Yeah, this is a good question. In the single metric one with the Jensen-Shannon, those two bars, they are done completely independent of the model. So they're done beforehand. But the Bayesian optimization approach is dependent on the model. So it's kind of a wrapper where you do data selection with the model, and accordingly, you also need a small depth set to be able to do that, which is kind of a downside of the method. Yeah?
Okay, I see. Thank you.
Yeah. But maybe I should add, most of the work is actually a priori in a lot of the cases. So you don't need the model at all at that stage. But you could link the two, of course, like we did here in this work. Very good question.
Yeah, so to separate them is because of the non-differentiability cases, or why? I mean, which one is better actually?
Yeah, good question. So definitely start off with the simplest, non-model dependent, like this Jensen-Shannon divergence, which is very good often, and then build up on that. But it's mostly an empirical question whether it's better to, because in a way, the simple ways disregard the label, right? They are only looking at the input actually. And the model is looking at the labels as well, so it gets more signal. But if I think back at these results, it's quite expensive to run actually, right? So it's and the results were sometimes it's more like interesting side effects also that you learn about what this means for these domains, even how close they are. But from a practical perspective, there are probably even leaner methods out there to look into.
Okay.
Somewhere in between these two, I would say.
Okay, thank you.
Yeah, sure. All right, then if you are okay, I would go to the next part, right? So this is now about cross-lingual learning. And here we are interested in essentially transferring a multilingual BERT model or one of these big pre-trained models to a set of new languages for a very specific task, namely spoken language understanding. And so that is actually one of the first tasks if you think about these voice assistants, right? So here I'm just plotting what are the languages covered roughly in 2020 for the big models, like the well-known voice assistants. And we see that there is some coverage, but there's still a long way to go. Maybe if Turkish is now included or not. Probably it is by now. No, not yet. Okay, so there is still really a lot to do, right? Even just in Europe, if you think. And so the question is, how can we transfer knowledge to these, to new languages essentially for spoken language understanding? Overall, this is cross-lingual transfer. There's a lot of approaches, but if you think about roughly trying to cluster them into big pots, we can think about one is annotation transfer, and there you have high resource languages for which you do have annotations, say English, and you have parallel data, and you can try to transfer the annotations from the English to the other low resource languages, or multiple high resource languages to the low resource languages. And we will compare to that in this model, but we will focus here more on the model representation work and start from a multilingual embedding model that essentially the transfer happens at the representation stage. Now, what we here looked at is how can we, or how beneficial are auxiliary target data sets or our auxiliary sources for transfer. So we're starting from BERT or XLM, and then look at the target task, spoken language understanding. I will come to it in a second, but then also to a set of auxiliary tasks. And so in fact, here we exploit the multitask learning. So we are assuming instead of having, two separate tasks, we are sharing parameters in order to have, say, the main task, spoken language understanding, and some auxiliary source that helps us to solve the main task. So you can see this as the main and auxiliary task as these different heads that you can have on top of your model. And here we were interested in thinking back. I'm not sure if you see it actually, because here is my video, about the availability of sources. In this work, we just assume that we have English target, English source data, English label table, and then we transfer to target languages, but we don't assume any in language data. So we're really focusing here on a zero-shot setup, and so we were interested in targeted multitask learning. And what do we mean with that? Using data sets or sources which are out there available for the target language, but which are not annotated for the target task at hand. So we tried one obvious case, masked language modeling, right? At the same time as the source, the main task. We also tried doing machine translation while learning the main task, and parsing, because UD is really huge, contains a lot of languages. Can we actually use parsing data to improve on this task? And so the actual task is this slot and intent detection task. Here is an example where the idea is, or the main goal is to do two things to find out what's the intent of the utterance and also identify these slots. And when we started this work some time ago, we saw that there is actually quite little non-English data out there. And so we were interested in essentially creating a corpus for more evaluation purposes, more languages. By doing so, we developed this new data set, which we call multilingual slot and intent detection. It's available on my postdoc's JIT Bitbucket site. And it derives from two sources. One is the SNPs data set, which is available only for English. And one is the Schuster et al. From Facebook back then, 2020, I think, or 19, I think, sorry, 19. We took these two sources because the Facebook dataset comes with 3 languages, but the SNPs comes with only one, English, and we homogenized the annotation so that we could create annotation guidelines, first of all, but also get data in different languages. So here are examples of the 13 languages we have included in the end. And notice this happened with, so to say, colleague sourcing. So we started off with languages spoken in the lab, German, Danish, Italian, Dutch, Serbian. And then we added more and got into it, we added more with colleagues who helped in this. So this is translation plus annotation, all manually done by people involved in the project. So as experiments, we run a multilingual BERT model, which is actually implemented in this toolkit, MatJump. And then the main baseline is to do the slot and intent sequence labeling. And we compare that to a strong baseline from the literature, which actually does machine translation with attention to do this annotation mapping directly. And then these are the results, actually. I'm jumping right into them here. And what we see is results in English are actually very good, right? It's a very high score for slots now. This is F1 score. The languages are ordered by similarity to English, as derived from Lang to Vec, except the first, which I will come back to, which is a low resource dialect. And what we see is actually, zero-shot transfer, the only task which really helped consistently to most of the languages was this auxiliary MLM task. So from the others, we saw not very helpful results. Sometimes they helped, but most of the times they didn't. But just, training on English and still kind of keeping learning the language was helpful in this setup, which is a nice way of kind of cheap transfer, I would say. If we then look a little bit more closer, so AUX LMM is the best model, which outperformed the baseline. But if we look at the NMT transfer, which wasn't very good in slots for the strict F1 measure, if we loosen this up and look at, hey, what happens if you disregard the labels? The picture is similar. But if you then loosen it up even more and say, okay, what happens if you just get the label right, but the span is not correct? So that's what we mean with loose F1 here. We see actually that the NMT transfer model, which is the strong baseline, is actually quite good. It just isn't correct in the spans that we are seeing. So I think there's more to be done in this direction to explore methods here for transfer. What we also saw is that on the intent, so the class label, sentence label, then the NMT transfer baseline was unbeatable. That's very strong. That was very good, which was also found in the early literature. The other methods don't work so well on the class prediction here. But overall, that's also the most expensive resource. So training that whole NMT system, it's quite intense if you compare the training times compared to adding these auxiliary tasks to the model. And finally, I want to come to this little detour on a very low resource German dialect, because this is really an example where we don't have much unlabeled data even. So we have one language or the language variant, which we include, which is South Tyrolean. South Tyrolean is a German dialect spoken in northern Italy, essentially here from that area. And it's, it's actually a trilingual area where there is a majority of German speakers. And as you might guess, this is actually where I'm from. So direction of where I'm coming from. But it's a dialect where there is also other languages like Italian and Latin are spoken, as you see here in the plot. And so South Tyrolean is a dialect which is derived from South Bavarian and living in this, approximately 500,000 people in the northernmost Italian province. And what is interesting also is it has a high influence of other languages like Italian and Latin. So if you have this example here, the boldface word means driver's license, which in German would be Führerschein, but in Italian it's la patente, and it's actually closer to the Italian, right, than the German variant, for instance. And even the gender switches, so it's really a mix a little bit of the two. But most importantly, this has no common orthographic standard. So I recruited a friend who helped out in the study, and you see here that is it going to rain today? The today can be spelled in different ways. It's very inconsistent spelling, even within a single translator in this case. So this is a problem of really low resource language or dialect, and we try to get unlabeled data, and even that is a challenge. So Twitter is not very much used, and if we find data, it's highly mixed with other languages. We don't have a dialect classifier for this type of variety. But we found another source, which is Ask.fm, where there's discussion posts by young adults, which are targeted about, they post questions there and they post their replies. So here are two samples from these two sources, just to give you an idea. Here, for instance, this is one user and we see some dialect, but we also see some Italian mixed into it. And the other one is more about these question answers, which are more casual but cleaner dialect. So we tried also, and we're interested, okay, how does it transfer to this low resource dialect? And now if you take the baseline with MBirds, we actually get 49% F1 on the slots. And now what we saw is actually we got quite a huge improvement by only a very tiny amount of unlabeled data. So these are 30,000 sentences that we added from these two sources. But it's interesting also to understand, okay, how much does each source contribute? So we had less of the Ask.fm data, so 6,500. So this is actually already helping. If you take a similar amount of Twitter data, that's a little bit worse, but still, altogether helps the most. So Twitter data was not, the closer to the language you can get, the better it is essentially, and not a huge effect, but still it's 23,000 versus 6,500 items here that helped in this case more of the Twitter data. So takeaways from this study is that we proposed this new exit dataset for evaluation of multilingual intent and slot detection. We found this auxiliary MLM task to be quite robust for cross-lingual learning. I would like to note that there is actually a simultaneous study that focuses on cross-domain transfer, and they propose a similar auxiliary MLM proposal or direction for domain adaptation. It's nice to see. And we've showed some first results on this very low resource German dialect. The data and code is all available. And I would like to point you also to the video. So this is the NACL video, and you can see all of the authors who contributed also to the study. They are showing up in the video. So, all right. All right. Then if you are still there, if you have any questions, please let me know. Otherwise.
So Barbara, I have a question. So here you explore these auxiliary tasks in isolation with each other. Did you also try multitask learning setting where you include more than one?
Yeah, this is a good question. No, we didn't. We didn't combine them. But maybe one note: the parsing task is essentially also a multitask model. We did parsing in the kind of UDFI style, which is in itself predicting all the single. But we didn't compare. No, we didn't. It would be the MLM plus the others, maybe. But no, we didn't see so concrete improvement from the other than the MLM. So the parsing and the machine translation auxiliary task weren't that helpful, so we didn't go further in combining them.
I see. Because in the multimodal word models, I think people are trying adding these multiple tasks during pre-training, so that's why.
Yeah, exactly. Like this massively multilingual, multitask models, right? Yeah, actually, this is the original motivation of going into this direction was essentially also like massively multitask learning. But it's also very tricky that you need to, also balance the task because you have different sizes, right?
Yeah.
So it's, I think there needs to be a bit more work in actually perhaps estimating a priori what is helpful before running all this experiment, because already these took quite some time on having several runs per number that you see now to have some stability across the data sets, since it's a zero-shot evaluation setup. Yeah, that's a very good point, in fact.
Thank you.
Yeah. All right, then last bit, I hope you're still with me. I will go into something different here, but still multitask learning will come up. So essentially learning with disagreement. If this is joint work with many people as well, and work that we with some have started much earlier as well, and we have now recently come back to this with Massimo Paesio and Dirk, in fact, and working together in this direction. But as you probably all know, if you do any kind of annotation project, you see disagreements, right? These are everywhere. And typically we try and to resolve them and find, annotations with a single interpretation, preferred interpretation. Although there might be differences in the annotators where there are multiple interpretations very, very plausible. So in fact, even for linguistically, even for linguistically more objective cases like boss tagging, we observed, or even, we know that like Manning's paper is a really nice study of this. There are hard cases where it's hard to clearly decide on what is the part-of-speech tag, even for a token. And so here is just an example from the actual data set where we see anything annotated with the 3 different kinds of tags. And so what can we do with this? Well, we can try to make the annotation guidance even stricter and come up with a gold label, right? Or we can also try to say, okay, hey, maybe there is just no single ground truth out there, and we're trying to embrace this variation essentially. But so some time ago, when we started looking into this, we were also interested in, hey, is this actually something which is a bit more systematic, or is this just randomly distributed? And so if it's systematic, it can be estimated from some small samples. And so back then, we did a study on looking at part-of-speech tags and their confusions on doubly annotated data. And back then we had rather small samples for this. So we annotated disagreements, we annotated data independently and then looked at these confusion matrices. And what you see here, for instance, for these two, we see that there are, similarities between them. So like adjective nouns or particles and adpositions are something which are regularly confused. There are even some more domain-specific or medium-specific confusions which don't appear so much in, say, the other domains. But we do find some regularities here. So then, knowing that there is some systematicity to this, how can we exploit this information? We'd like to notice that this is actually a huge area in itself. And, there is, like, broadly speaking, you can think about modeling it, right? Embracing it. Or you can think about fixing the data, or even there are proposals of trying to filter the data and just learning on, the good cases and trying to filter out the hard cases from the data set. But here we are trying to take this algorithmic approach and trying to see if we can embrace it. And this is what I mean, this is one example of what we would call a fortuitous data, because we often don't use this kind of information in our modeling. So it's kind of data out there which we can make use, but often don't. And so fortuitous data is a more broader concept, which you can think of data that can be harvested. So it depends on the availability, but it can be used maybe with different kind of degrees. How ready it is, it depends on which kind of fortuitous data you're thinking of. And just to give you some examples, annotation disagreement is like one type of what could fall under this fortuitous data sources, which is not so much available, but it's quite readily usable for our models. This just to contrast with more other benefit or side product, like when we have human data from human processing, like gaze or keystroke or other cognitive signals. This is also kind of fortuitous data, but it's perhaps more available, but it's not very readily usable. You need to do some steps first in order to be able to use it. All right, but back to disagreement here. How can we exploit this? And as I mentioned, there's a lot of other related work. I just cherry-picked, to be honest. One is the earlier work by us in 2014, where we looked at boss tagging and these confusion matrices that I've shown you earlier. And the main idea here is essentially doing a cost-sensitive learning. Whenever you update your model that you train on gold data, you look into this confusion matrix estimated from a small sample and say, hey, this confusion here is actually something that my annotators also found difficult. So let's update less on this case, so integrate it in this way. But one drawback of this is it's a quite static view, right? It's an aggregated global confusion matrix which doesn't depend on the instances itself. So we were recently interested in, hey, what if we really had multiple raw annotations? Can we exploit them in training? So that we didn't have that back then, essentially. We only had a small set. So, and in particular, can we use this with multitask learning? So normally we have human annotations, right? We ask our annotators, and then we are interested in deriving some gold label. And in this work, we are still using the gold label as kind of the main part to learn from, but we want to embrace that sometimes annotators disagree. And so the typical setup with gold labels looks as, you might imagine, you have your model and you get your softmax, for instance, and then you observe a gold label, you do cross entropy loss, but then you backpropagate essentially, typically the gold label, the label depending on the single gold label, the loss depending on the single gold label, sorry. And what we propose here is to include the soft labels as a kind of auxiliary task in multitask learning. So this is joint work with Tommaso, Fornaciari, Alessandra, Silvio, Dirk and Massimo, and we do a multitask setup where we learn the same as before, an auxiliary loss with the gold labels, but in addition we add these, annotation divergences into the model with an auxiliary loss, which compares the softmax to the annotation distribution. Now, of course, then how do you compare, right? There's various ways, and we looked also at various ways to do so. But what we found worked quite well is actually just taking the KL divergence between the two distributions. And what we did in the paper is we looked at two tasks, post-tagging and stemming. We compared it to single task setup and also multitask setup with gold labels and with majority vote, and then integrating the soft loss. And what we saw is essentially, these are results for two post-tagging setups and the stemming setup. And what we saw that this helped us quite consistently in adding the soft labels to the model over the single task model. It depends a little bit on the direction because KL is not symmetric, but the one where you assume that the annotators agree, which is more peaked, that's actually the one which was better, slightly better for this task. So this was like a short run to this kind of work. And my main point here is that, there is this disagreement. This is not all noise. We might be sometimes better off in embracing it. So if you are doing annotation projects, it would be really great to also get the raw annotations to allow this kind of work. There is much more to be done. We are actually, there's a huge literature also related to noisy labels, which taps into this. But also another aspect is we are still evaluating across against gold labels in this setup, which you might think, is that the right way to do? And so we have actually an upcoming workshop paper at the ACL workshop for evaluation, past, present, and future, where we argue we need to find better ways of evaluation and also understanding these different forms of disagreement across different tasks. They are very, very different and might be stemming from different factors. So to wrap up, I've tried to give you an idea of the kind of topics that we are studying here, are interested in, with 3 selected papers. And maybe just to wrap up, I've talked about the 2 last boxes, transfer learning and fortuitous learning, which are all about like lack of labeled data, right? But this is yet again a small area in a huge field with a lot of other approaches out there, which go more into generating additional labeled data, pseudo-labeled data. So I think it's actually a very exciting time to study this kind of methods and to see how we can best address scarce and biased data. And with this, I actually would like to thank my collaborators and also the members of my lab here. And I'm very much looking forward. And thanks again for this opportunity to talk to you here.
Thank you, Barbara, for this really interesting talk. So I have a question, but let me first ask the audience. So does anyone have a question to Barbara?
I have a question.
Yeah, go ahead, Osman.
Yeah, thank you for the talk, Professor. I was wondering about your like insights or about model selection in domain adaptation, actually. Because in your paper that you showed, you said we use some label data from target domain, right?
Yeah, that's right.
So like especially in unsupervised domain adaptation and domain generalization, like that is a huge problem. If like how are you going to test your model, especially like when hyperparameter tuning or something. So do you have any insights for that? Because I'm currently working in that area. I would love some, ideas or.
This is a great question, because this is in fact a huge problem in both both dimensions, language versus domain, right? This is kind of this analogous, and you can even see them as one thing, right? I tease them apart, but that's not really what you should think. No, right. In this work, effectively, we assumed labeled def data for the domain. I think we did it for the target, 100 sentences in the target domain, which is a downside, because this is not a realistic setup, in fact. In follow-up work, a year later, we looked at semi-supervised methods and also did similar experiments, but then we proposed to assume just one domain def set from one of the domains as kind of the tuning set. That's the 2018 paper, and I think that's cleaner, to be honest. If I would go now back and ask you to or you work on this, I would assume that setup.
Like a different domain other than your source or target.
You would choose either a source domain, or if you can also choose one target domain as a labeled def set.
I see.
At least that's kind of analogous to. It depends, right? Back then we did so in that setup, it was really about transferring from all pairs or all setups, and then we just said, okay, one is the def.
Like one of the experiments that you ran show the domain similarity thing that you ran. Like if you select samples that are similar, that are from similar domain to target, like maybe you could select your extra domain to dev set on or something. That would be, I guess, a way.
Yeah, actually, I would really love to take this discussion further, because this is a problem I was recently just even reading up on what's happening in the literature, and I would really love to brainstorm about that and finding better ways. What you say is one concrete suggestion, right? Because there is also been recent work on showing that if you do cross-lingual transfer and assume only source language def set, you're actually underestimating the performance, right? There's this paper by, you probably know it, Kong et al. From the UNLP, and they proposed to choose the checkpoint on assuming target language data as a kind of oracle, right? But it doesn't solve the problem. It's still like, how would you get automatically to choose this good stopping point? Or in fact, this is a very interesting question.
I actually recently I saw a paper from, I guess it was Facebook, called Domain Bet. They started a kind of a dataset challenge repo that they created with multiple datasets, and ran some baselines on it with different model selection methods. If I can find the link, I can send you.
Yeah, perfect. That would be very interesting. Yeah.
Okay, thank you again for the talk.
Thanks for the great question. Really interesting. That absolutely aligned to what I'm very interested in. So. Great question.
So I see Amit is raising his hand. Amit.
Hello.
Hi.
Okay, I'd also like to thank you for the talk today. It's been really enlightening. And my question is related to the last section about fortuitous data, especially, let's say, disagreement between annotators. You see, I'm part of a sort of mass annotation project. It's non-academic, so it might not go anywhere at all, but I might as well mention it anyway. And basically, we're marking ad sections during YouTube videos, because now instead of the default ads, people also have sponsors, right? So the, people might viewers might lose 3 minutes watching an advertisement when they might have just wanted to watch a tutorial. So the goal of this project is to see if we can train a data set to automatically detect sponsored sections in videos. And there are many annotators who are working on this, and it's not academic, so almost zero organization, but there's some organization. So my question is, in the example you gave us, where for POS tagging, where you try to exploit the probabilities, obviously some disagreement is going to be due to variation because people hear or understand things differently, but some of it might also be due to maybe absent-mindedness on the part of some annotators. So have you ever considered maybe having 2 rounds of annotating, one where everyone gives a first guess and then you expose what frequency has a certain part of speech has been marked, and then ask them to annotate a second time to see, to make sure that they haven't messed up on the first one.
Yeah, that's as well right. So yeah, thanks a lot. Interesting what you're doing with the like friend sourcing. I can imagine with the ads. A cool project. No, we didn't do 2 rounds back then. Would be interesting. It's a though very difficult task, difficult problem to get to know why they then. So let's say now this work still assumes that the annotator in itself is consistent, and you're hinting at this problem. Actually, annotator by him or herself might not be consistent even, right? And we actually do know that this happens, but and I find it a very challenging issue. But what could we do to get beyond this? So we might need some other information about, are they looking at the screen, or what are they looking at their phone, or I don't know, some sort of extra information to be able to, or the heart rate, I don't know, really just thinking out crazy things. There is not so much in that direction as far as I'm aware of. If anyone knows about modeling annotator, there is of course modeling the trust of the whole annotator as such, but if there is much more in modeling the annotator on whether they are still paying attention, or where are they in the process of annotation, right? How far is it? Just at the beginning you might be more attentive than towards the end of the hour if you do it for an hour or whatever. Not sure if there is much work in this from an NLP perspective, at least, or maybe more from other fields perhaps, that we find some more ideas. If you know,
there was this large Stanford's image data set. I can't remember the name, but it was basically being annotated by only 1 student, so it wasn't actually super difficult for a machine to beat them. It was like 95% versus 92.5 on the human's part, I think. So yeah, obviously humans have some natural threshold if they're only doing it alone.
Is this maybe the one by annotator? Are we modeling the annotator? Are we modeling there is one paper that is about generation of data, where they show that we are essentially modeling a single person, right? Which is also related to this issue, right? Mm. Is this maybe the one you are thinking of, or?
No, I don't think so, but that sounds interesting too.
So maybe this is somehow also related to active learning as well, like choosing samples to annotate. That there may be some work on that.
Yeah, true. There might be some work in that direction. but perhaps more in the human-computer interaction area, perhaps. I don't know.
Yeah, I think a human in the loop type system.
Yeah.
Mm-hmm.
Okay,
so
thank you.
Yeah.
I
I think it's interesting to, if you can afford doing do 2 rounds, it could be very interesting to look at the divergences of the annotators. Could be interesting question to look at.
Mm-hmm. So basically, I also think something similar, like this rounding idea. So this reminded me of this old nonlinear methods, random forest and boosting, where each round you train a different classifier. But here, these so-called weak classifiers just see only the annotators from a single person. That makes sense, or yeah, like this is like an ensemble learning, but each model just is trained on a different set of labels, basically.
Yeah, that's a very good intuition. And there is even work which I haven't mentioned, but there is even models that essentially add like a annotation layer similar to, so they added actually on top of the gold label, where they model each annotator as a separate task, and it's called deep learning from crowds, where they try to keep the single annotator as a top instead of we now aggregate it as a distribution, right? So that's a bit of a different take. We have some follow-up work which is not yet out, but in which we compare the different ways, and also across not just NLP tasks but also computer vision tasks. So like this CFAR10H set. And so far there is no best method for all of the tasks. It's really depending on the task. And for this vision classification task, that kind of model was one of the best, at least for one of the data sets. Whereas the single task learning, the multitask learning we proposed was better for 3 of the NLP tasks, which were actually a couple of more, even textual entailment was one of them. But yeah, I think there's much more to be done in understanding this and modeling it. This is a nice analogy that I haven't thought of, the boosting methods and the old good models. So it's a very good idea to think back in the traditional bootstrapping kind of
exactly
models. Yeah, great.
Okay.
Are you doing anything in this direction as well, or?
No, not really. Because I just think of this. I taught machine learning courses like for a long time, so that's why maybe it reminded me of that. Okay, maybe I can ask one last time. Are there any questions to Barbara? Okay, then I think this is it. Thank you, Barbara. It was really nice to see you and listening to your talk. Hope to see you soon face to face.
And let me thank you again for the invitation and everyone here for attending, and really very interesting questions. So thanks a lot for the invitation. The pleasure is on my side.
Thank you. Good evening.
All right.
Barbara.
Take care. Good evening, and hope to see you soon as well.